Oh, okay.
Let's start. It's my pleasure to have Chengze here from University of Maryland, and he's gonna talk about perfect submonoids of dominant weights and the characterization of reductive monoids.
Okay, so thank you, Huanchen. So hello everyone. So it's my pleasure to give this talk here at NUS. So so let me share the. Hopefully this won't be too bad for you. So I'm using something like the document camera. So today I'm going to talk about something called perfect submonoids of dominant weights and its relation with let's see, I'll just use comma, and its relation with reductive monoids, and maybe maybe I will talk about more about like Windbreak monoids and such things. So I will talk about this.
Chengze,
so
excuse me, could you write the letter a little bigger?
Oh, okay, sure.
Yeah.
Sorry.
Thank you.
So this first definition, this perfect submonoids of dominant weight, so this might be, so it is not used very often. So as far as I know, so I think it first appeared in Windbreak's paper. So in his work on reductive monoids and Windbreak monoids. But however, this can also be viewed as a definition in representation theory independently of the connection with algebraic monoids. So today I'll just start from the representation theory side and then move on to the algebraic monoid side. All right, so let me start from part one. So the part one and part two are just the representation theory side. So part one is the tensor product decomposition. So this is just so I will recall some features in representation theory. So let me fix some notations first. So let G be a connected reductive group. So connected reductive group over K, and here K is an algebraically closed field with characteristic 0. And we fix a maximal torus of G. We fix a maximal torus T of G, and we denote the root datum by the quadruple, by this quadruple. So this be the root datum. So this for the weight lattice, for the co-weight lattice, and the roots and the co-roots. So we add a plus here for those dominant elements, and we denote by alpha I the simple roots, and omega I the fundamental weights. And we know that finite dimensional irreducible representations of G are parameterized by dominant weights. So we just denote them by this L lambda. So this is the irreducible representation of G. So with highest weight lambda. Okay, so these are some notations. So the feature I want to talk about first, so I want to recall the tensor product decomposition. So the tensor product decomposition is a natural problem in representation theory, and it has been studied for many years. Oh, sorry, I missed an I here. So namely, just due to the complete reducibility, so we can decompose the tensor product of two irreducible representations into a direct sum of representations of irreducible representations. So namely this one. So this is tensor product decomposition, and the multiplicity here, this m lambda mu nu, are called the little Richardson coefficients, or we just briefly called it tensor product multiplicities. So there are two major concerns for this tensor product decomposition. So the first one is about the components on the right-hand side, and the second one is about the multiplicities on the right-hand side. And actually, the first one is contained in the second one because it's just about those non-zero multiplicities. So both these two problems are quite hard, but here today we only focus on the components. So we define the following set, x lambda mu, to be the set of those components appeared here. So namely just those dominant weights nu, such that L nu is a direct summand of this L lambda tensor L mu. Okay, so, I think I should, yes. So this is the set x lambda mu. So there are two important results on this x lambda mu or on this components of tensor product decompositions that we need to use later. So two important results.
Excuse me. We cannot see your what you are writing.
I think I have to zoom out a little bit. Wait for this. Is this better?
Yeah, it's okay. Looks okay.
Yeah, maybe I will just keep like what we did in Maryland before, keep a forbidden zone here.
Yes.
All right. Wait a minute. So now, now you cannot see what I'm reading. So two results. So the first one, I think I'll move it like this. I think it's not good. What can I do? Is it okay, or I will just keep this one to be the forbidden zone, this top area from this part. Okay, I will not write on this part. So there are two important results on this tensor product decomposition on these components. So the first one is the Prv conjecture. So the Brb conjecture, so let's recall this conjecture, that is, so if you have two dominant weights, lambda and mu of G, then we have for any element W in the bio group, the dominant weight lambda plus W mu bar is containing X lambda mu. So here, this dominant weight, this lambda plus W mu bar is a unique dominant weight in the bio group orbit of this lambda plus W mu. And this is a characteristic zero case, zero version of Prv conjecture. And it was proved by Kumar first, and also Lustig, Rajeshwari, and Littleman, they also gave different proofs separately later. And this conjecture also have a positive characteristic version. So that was extended by Mattia. And it says, okay, so for this one, from this, we know that L lambda plus W mu bar is a direct summand of this tensor product. And in a positive characteristic case, what we have is actually L lambda plus W mu bar is a subquotient of this tensor product. But we don't need that. We don't need that today. And the second one is a counterpart of Vow's conjecture, or Vow conjecture, whatever. And it is also proved by Kumar. So let's lambda and mu be two dominant weights of G, and beta be a positive root. Suppose that we have the following two conditions. So first, lambda plus mu minus beta is still a dominant weight. And secondly, the union of S lambda with S mu is containing F beta. So here, S lambda or S mu, same thing, just a set of simple roots of I such that lambda of I check. So this is the corresponding co-root. This is 0. And F beta is the set of simple roots such that beta minus of I is not a positive root and not 0. So if we have these two conditions, then we can say that actually lambda plus mu minus beta is in this set x lambda mu. So this sometimes is called the root component of this tensor product. Okay, so these are two important results that on this tensor product decomposition, and the two results that will be needed. We need to use later. So we just keep these two results in mind, and then we can move on to the second part, the part about perfect submonoids of dominant weights. So part 2, perfect submonoids of dominant weights. Okay, so let me first define this. So a submonoid L of dominant weights is perfect if we have the following condition. So for any two dominant weights lambda and mu in L, the set x lambda mu is contained in L. So if we have this, then it is called perfect. And we can notice the fact that actually this being perfect is to say that L, so this is to say L perfect is actually saying that L is closed, undertaking direct summons of tensor product. So this is somehow a type of closeness for this submonoids of dominant weights. Okay, so let's see some examples. See some obvious examples of this kind of perfect submonoids of dominant weights. So let's Q be the root lattice of G. So example. So the first one, so obviously you have that the zero submonoid, right? The zero set, or just the set of all dominant weights. So these two, they're definitely perfect. And the second case, the second example, like if you have L is the intersection of L tilde with dominant weights, and here L tilde is a submonoid. Oh no, it's a sublattice of the weight lattice containing the root lattice. So if you have L is the intersection of a sublattice of weight lattice containing the root lattice intersect with the dominant weights, then you have this is perfect. So this is because like any dominant weight nu in x lambda mu can be written as lambda plus mu minus a positive integral combination of roots. So you have that is in Q, and then you will have that because that is dominant. Then you have that is in L. And later we'll see that actually this the general case is somehow related to this case, but not exactly the same. Okay, so these are two basic examples, and now you can still see this, right? And now, before we talk about more about this, about characterizing, finding these perfect submonoids, let's first see some properties of this. Okay, so let me make a forbidden zone here. All right. So let's look at some properties of this perfect submonoids in representation theory. So some properties. So as we mentioned here, actually this perfectness is somehow type of closeness. So let's look at some other types of closeness. So here let X be a submonoid of dominant weights. but not necessary to be perfect. So we don't require it to be perfect. And we look at other two types of closeness. So called by C1, the first type. So that is for any dominant weight lambda in L. So the dominant weights in pi lambda. So this is contained in L. And this pi lambda here is the set of weights of this irreducible representation L lambda. So this condition is somehow saying that this submonoid is closed under taking dominant weights in this pi lambda, where lambda is something in L. And the second type here, denoted by C2, is that, okay, for any dominant weight lambda in L, the dual weight lambda star is in L. And so this is saying that L is closed under duality. So, and we also take our perfectness here. So these are three different types of closeness can be viewed in that way. And our first question here is, are there any connections among them? So to do this, and also for convenience in this whole, I think for this whole part, not exactly, yeah, for this whole part, I would like first to.
Can I ask a question?
Yes.
What is lambda star? I didn't catch up that.
So this is a dual weight of lambda that is W0 negative lambda. So this W0 is the longest element in the bio group. So namely, this is just the highest weight. This is the highest weight of this dual representation of L lambda. So question is, are there any connections? So we would like to first reduce our discussion to the case when G is simply connected. So to see this, actually, I don't want to waste too much word on this. So actually, if G is not simply connected, then it is isomorphic to its simply connected cover, GSC. So this is a simply connected cover of G, quotient by a central subgroup Z prime of GSC. And in this case, G and GSC, they have the same root lattice. And for the weight lattice of G, X over star T, can be viewed as a subset of the root lattice, a weight lattice of GSC. So consisting of those weights, which is trivial on this central subgroup. And moreover, for that tensor product decomposition, what we need for perfectness, that is this little Richardson coefficients are the same for G and GSC. If we have lambda mu nu, they are dominant weights of T. Dominant weights of G. Then this multiplicities are the same for G and its simply connected cover. So actually, we can pass our conditions, all these conditions above, just to the case when G is simply connected. So from now on, we assume G is a simply connected group. And we'll first start from the case when G is semi-simple. So we first assume G is semi-simple. And our theorem, so our first results about for this question, but that's not the complete result. So that's the first result for this question. So that is my first result. So theorem 1. So suppose that G is semi-simple and L is a perfect submonoid of dominant weights, then L satisfies C1. So this is my first result that claim this perfectness implies this C1, this type of closeness. So if it is perfect, then for any lambda in L, all the dominant weights of in pi lambda is contained in L. So this is the first result. And actually, this is, let me briefly state the strategy of the proof of this theorem. So actually, this is based on the following proposition, following property. So the proposition. So let lambda be a dominant weight in L. Then there exists a dominant weight, omega lambda in L, and a positive integer m, such that mu plus m omega lambda is in L for any mu in pi lambda. So this proposition claims the existence of at least a translation of this set is in L. So let me make some remarks on this proposition. So first, actually we can further require this omega lambda to be somehow nice. That means to have some sort of regularity, and I will explain this later. And the second one is that actually we can notice that both omega lambda and m, they depend on this dominant weight lambda. But the thing is, actually this omega lambda can be not very dependent on lambda. Okay, so I'll explain this two remarks now. So actually, as we assumed G is semi-simple and we already reduced the whole part to the case when G is simply connected. So actually, for this G, we can write it as a product G1, G2 until Gn, where each Gi is simply connected and simple. So we can also write the weight lattice and the root lattice as a direct sum. So each x upper star ti is the weight lattice of gi, and qi is the root lattice of gi. So under this decomposition, we can actually write any weight in x upper star t as an tuple. So each pi I lambda is in the x upper star ti. So now we say that lambda is called k regular if we have this pi k lambda is a regular dominant weight of x upper star plus tk. So regular dominant weight is just, so for dominant, that means lambda of I check is greater than or equal to 0 for all those simple co-roots, and if it is regular, then that is strictly greater than 0.
Can I ask a question?
Yes.
Yeah, in your proposition, m, the positive integer, is depends on lambda, right? But it's independent of mu.
It's independent on mu. So these two, but both omega lambda and m is independent of this choice of mu. So it's for any mu.
Okay, thank you.
So we choose this two, and then it's for any mu.
So this omega lambda could be equal to 0, right?
This omega lambda could be, you mean it could be equal to 0? Okay, let me think about that. So actually, it could, I think, yeah, it could be equal to 0. It could be, no, it cannot be equal to 0, because if it is equal to 0, because in this pi lambda, this is just a set of weights, not a set of dominant weights. And if it is 0, then definitely not. Yeah. And actually, we needed to have some sort of regularity. So that is what I want to explain here. So actually for this remark one, what we have is, for this remark one, what we have is for any k between 1 and n, so that's for this, it's the index set for this component. So what we have is, if pi k lambda is non-zero, so pi k lambda is a non-zero weight, non-zero dominant weight in x upper star plus tk, then we can require, or we just require, we can require omega lambda to be k-regular. So in particular, if this is non-zero for all k between 1 and n, so then we can just require omega lambda to be a regular dominant weight of G. And for the second remark is that actually this omega lambda only depends on the set, this following set, that is the set of k between 1 and n, such that this is non-zero. So, so this is what we need. Actually, we don't need this second remark. I just want to say this is not, it can be not very dependent on lambda, but we need this first remark for this theorem. So, based on this proposition and this first remark, actually we can give the rough idea for this theorem one, for the proof of this theorem one. That is, so for any dominant weight mu in pi lambda, we want to construct another dominant weight, maybe not another, just construct a dominant weight eta in L based on omega lambda, such that mu plus eta is in L and W0 eta is equal to minus eta. And if we have this, then by Prv conjecture, we will have that mu is mu plus eta plus W0 eta, which is contained in X mu plus eta. Oh, no. Oh, yes, mu plus eta and the eta, which is contained in, which is contained in L.
Okay, thank you.
By perfectness. And the construction of this, so what I said by construct eta based on omega lambda is that actually we apply Prv conjectures for several times, not only on omega lambda and on its outcomes, and on that actually we'll get a sequence, and by applying Prv conjectures for many times, we can finally get what we need for this one. And the construction of this eta is actually somehow, and that needs the k regularities. So there's some certain k regularities of this omega lambda. So that's why we want to require it to be k regular. And also the construction of this eta, so eventually it will reduce to the case by case argument, which is really technical. So I really don't want to talk about that here. Okay. So this is our first result, and this tells us there's a connection between these different types of closeness, and that is perfectness implies this C1. And we shall see later that actually this also implies C2, but that is based on our second result. Let me draw one here. So I think this part I can just cover it. I'll just leave this part here. All right, and also the forbidden zone. So this is the part about this different types of closeness, and the second natural question is, so how to characterize this perfect submonoids of dominant weights. So for this, let me first define the following thing. So let's still let L be a submonoid of dominant weights. Then we define the component support of L is the following set. So that is the number k between 1 and n, such that pi kl is not the zero set. It's not a set just containing the zero element. So this pi kl are just the set of those pi k lambda for lambda in L. And based on this definition, we have the second, so this is my second result. So let G be, to be strict, I should say, be simply connected and semi-simple. But actually this theorem, so this is the version for, I'll just write down the version for simply connected case, but there is a modified version for general case, but for that I need to define some more notations, and there will be some technical discussion, so I don't want to talk about that here. So I'll just talk about the simply connected case. So then the perfect submonoids of this dominant weights with component support sigma 0, which is a subset of this 1, 2 until n. So that is the index set for components, are exactly the intersection of L tilde with dominant weights, where L tilde is a sublattice of X upper star T sigma 0 containing Q sigma 0. So here for this two, actually the X upper star T sigma 0 are the dominant weights. Are the weights of T, weights of G, such that pi k lambda is 0 for k not in this sigma 0. And this Q sigma 0 are just the intersection of the root lattice with this subset of this sublattice of the weight lattice. So this is my second result about characterizing this perfect submonoid, and the proof of this theorem is based on our first result here, and we can, because this condition, this first closeness, is something easier for us to do the characterization, because the condition for a dominant weight lying in this set is the condition is more explicit rather than that tensor product decomposition. So we use this first result here to deduce this one.
Chengze, can I ask a question?
Yes.
I think maybe I'm just confused by the statement. So the component support, really you want to know which component is non-zero. So I mean, yeah, just looking at your statement, it's a subset of 1 to n. So what do you mean it's the intersection? I'm a little confused. Maybe just the phrasing is a issue.
Oh, so what I mean is, so the component support is something for a perfect submonoid. For a submonoid. So this a submonoid, a perfect submonoid with some component support, sigma 0, that means by this definition.
Oh, I see.
So for those k not in this component support, pi k l is just the 0. It's just the 0 set. So for those lambda, yeah.
So, my English issue. I break the sentence in the wrong place. Thank you.
So I have a question. Is like if n equal to 1 case, does that mean the perfect submonoid should be either equal to 0 or it's coming from some lattice?
Some sublattice. Yes. But this is for the simply connected case.
Yeah, for simply connected. If
okay. Yeah. And Sorry?
Okay, please go ahead. Yeah.
And yeah, maybe this statement is somehow, I should say, I don't know, it looks kind of nasty. So maybe we can look at some example. So let's take the example, an explicit example. So here, actually, let we choose G to be the product SL4, and S with SL3. And then we just look at those perfect submonoids. We just look at those with whose whose component support is 1 and 2. So there are 3 components. So we let that component support just be 1 and 2. And we know this is corresponding to those sublattices of X upper star T sigma 0 and this one. So basically just Q 1, 2 and X upper star T 1, 2, which is just isomorphic to X upper star T1 direct sum X upper star T2 quotient by Q1 or just X upper star T1 quotient by Q1 direct sum X upper star T2 quotient by Q2. So that is just somehow just the subgroups of this X upper star T1 quotient by Q1. Wait. And for this one, we know that for this 2, so these 2 are just the center of this 2. So it's just Z mod 4Z, direct sum Z mod 4Z. So it just corresponds to the subgroups of this Z mod 4Z, direct sum Z mod 4Z. So for example, like we can take A to be 0, 0, 1, 3, 2, 2, and 3, 1 of this one. We take this subgroup. This is a subgroup, right? Yeah. And then, so this one we let P be the natural projection from X upper star T 1, 2 to X upper star T 1, 2 quotient by Q 1, 2, which is isomorphic to this. So then we just take, so then we have L, which is P inverse A, intersect this dominant weights. So this is perfect. So namely, that contains those dominant weights and whose corresponding central characters, like central. If you view, you can also view this because this is just a center, so it is also the same as the center characters. So like a subgroup of that, which corresponding to on this first 2 component on this product, it takes this in that center. And for this 3rd component, it is not take 0 on that center. It is take 0 on the whole on that whole maximal torus corresponding to this 3rd component. So as I said here, actually we can somehow use this central character to see this. So actually I would also like to write down the reformulation for this one, which is somehow, I would say it is still under the same setting, which is easier to view because I think the central character is definitely better than just this sublattices. So there's the natural bijection. So this reformulation can be deduced from this original version just easily. So on the left-hand side are the perfect submonoids of dominant weights with, I'll just briefly just write the component support sigma 0. Okay, I use this to denote the component support, and with the subgroups of what we call Z sigma 0. So this sigma 0 is the subgroup of Z. Also, Z is the subgroup of the center Z of G. So because because actually in this case, this simply connected semi-simple case, we can actually write that Z as the product Z1, Z2 till Zn, right? So this sigma 0 is for those k in sigma 0, then we just still take those zk, and for those k not in sigma 0, we just force that position to be the identity. So then this bijection is given by this map. So if we have a perfect submonoid L here, then we have a subgroup of this sigma 0. So those elements Z in those elements Z in the sigma 0, such that lambda Z is 1 for any lambda in L. So you view, so you use this central character, view it as a central character, and this is just something like the vanishing subset of this subgroup. And if you have a subgroup here on the right-hand side, then you actually give this reformulation of this perfect submonoids. So that is all the dominant weights lambda, such that first lambda is trivial on this subgroup, and moreover, lambda is trivial on those maxima torus tk, where k for any k not in this component support sigma 0. So yeah. So, and one thing I want to say is, okay, I also want to mention that when sigma 0 here is equal to this 1, 2 until n, then we call this case to be the full component support case. So, because we will need to use that case later. So these are two results on characterizing this perfect submonoids. And then based on these characterizations, actually we have the corollary. So this corollary, as we said, actually this is just, we reduce this to the simply connected case for convenience. And actually this all can be viewed as, these results are actually for general G, not just simply connected. So now the corollary is suppose that G is semi-simple and L is a perfect submonoid of dominant weight. So based on this characterization, we have L satisfies that C2. That is close under duality. And so one thing I want to mention is actually, so here we used, first we proved L implies C1 first, and we used that to, and that is finally a case-by-case argument, and we use that to characterize this perfect submonoids, and we use this characterization to show L implies C2. Okay, and this was suggested by Professor Thomas Haynes that if we can show that L implies C2 directly, that means avoid all these above steps. And then by combining L with C2 I can remember one of his result before, then actually we can give a case-free argument for L implies C1. And that will be much nicer because our proof for that construction is really technical. But unfortunately,
So somehow C2 is stronger than C1. Is that what the conclusion? I'm getting slightly confused. Sorry.
Actually, the thing is, I want to draw that is actually perfectness. What I know is perfectness implies C1 and also implies C2, but actually I don't know any information about this too. But definitely we don't have these two. I think we don't have these two directions. I'm not sure, but the thing is, I don't know any information between these two. And what I want to say is, actually what we did here is we combined these two to get this one. So perfectness first, it implies C1. And because C1 will enable us to characterize this perfectness, so we didn't show this directly. We use perfectness and use C1 to characterize perfectness and then show C2. And actually Tom's comment is actually if you can show this directly, then we can give a case-free argument for this part. But that cannot say which one is stronger. So for this two.
I see. Thank you.
So this is for the semi-simple case, and the thing is for the reductive case. So let me move to the reductive case. So for reductive case, now we let G to be reductive, but not. So how many times do I have now? Like.
You can have until 11, like 12 minutes.
Okay. Because I haven't moved forward to algebraic monoids. So okay, I will just briefly talk about this reductive case. So what we have is, so let G be reductive but not semi-simple, and G0 be its derived subgroup, and D0, the upper zero be its connected center, and T0 is the maximal torus of G0. And we know that T is an almost direct product of T0 with the upper zero. So there is a natural bijection from X upper star T to this direct sum. Just by simple restrictions. And what we have is, maybe I don't write down as proposition. So the thing is, actually perfectness is actually linked by I. So actually the perfect submonoids of X upper star plus T, so on the left-hand side, are exactly the perfect submonoids of the right-hand side, but we need to add a plus there for the dominant part contained in the image of this I. So somehow this means actually we just need to look at those. We just need to look at the right hand side. Just need to look at this, and for that actually we want to write L in the following way. So let L be a submonoid of the right-hand side now, and let pi CL be the projection of L to the second component, and then we can write L as a disjoint union for those nu in pi ZL, and just mu where mu is in L nu. So here L nu is the set of those mu such that this is in L. And if we have this L, and if we have this L is perfect here, then actually we have we can deduce two properties. So first, L0 here is a perfect submonoid of this X upper star plus T0. So this is a perfect submonoid of dominant weights in the semi-simple case. So we can characterize this L0. And the second one is, which is L nu1, L nu2, which is the union of X mu1, mu2, where mu1 is in L nu1, mu2 is in L nu2. This is contained in L nu1 plus L nu2. So we have these two conditions, and based on these two conditions, we want to characterize the perfect submonoids of dominant weights for this reductive case. And what we want to use is that counterpart of Val's conjecture. And by that, we can decompose the general case into two cases. So just we need to deal with these two cases, and then we can have the general case. So the first one is L0, which is perfect submonoid of this one, has full component support. So this is a semi-simple case. So it has full component support. And this case is not hurt. And the second case is when L0 is just 0. And in this case, it becomes complicated. And this is not done yet. Because in this case, because one special case of this condition 2 is X L0 and L mu is containing L0, L nu is containing L nu. But what we have here in this second case is that condition is useless now because L0 is just 0. So this is still remain to be determined and not done yet. And also for those three types of closeness, and for that condition, perfectness implies C1 and C2, and this is not true anymore in this case. Okay, so this is part 2 about perfect submonoids of dominant weights. So about perfect submonoids of dominant weights, and basically those are so for those part 1, part 2, we only need representation theory. And now we want to move on to the next part. So the last part about reductive monoids. And from there, we shall see a Windbreak monoid. And we can see why this is actually this is another motivation for our effort in characterizing this perfect submonoids. So let M be an algebraic monoid over K, and K is still the same as what we have before. And let G be the unit group of M, and G0 be the derived subgroup of G. I don't know if it's nice to write it in this way. So now we assume this M is irreducible, normal, and reductive. That means it is an irreducible normal variety, and also this unit group G is reductive. So we know there is a natural action of G times G on M. So basically just G1, G2 act on this M this way. And then for this action, we can define the abelianization of this M. So basically 2 parts. So the first part is, we denote it by AM, which is the GIT quotient of M. So GIT quotient, M quotient by the G0 times G0 action. So which is a kind of sub-action of this. And the second part is a morphism. Okay, a okay. For this definition, it's just a, oh, sorry.
We cannot see that, yeah, thank you.
Yeah, oh, I forgot to give a forbidden zone this time. So
it's okay, I'll remind you, don't worry.
Maybe I should, yeah, but I think, oh yeah, but we don't need this part. We don't need that part later, so I'll make this for this one. So the second part is a morphism of varieties. So from M to AM, so it's just induced by the natural projection from this KAM to KM. So that's because this KM is just those G0 times G0 invariants of KM. So that's a basic property of GIT quotient. So this is the abelianization of this reductive monoid M. Actually, for this definition, we don't require it to be normal, but we just assume it to be normal for this whole thing because yeah. And then actually Windbreak showed that this AM here, it has a structure of commutative monoids, so that's why it gets called the abelianization, such that this pi M is a morphism of algebraic monoid. So moreover, actually this, for any map, any morphism of reductive monoid, it induces a morphism between abelianizations such that this diagram commutes. And in particular, if this diagram is Cartesian, then we say that phi is excellent. If this is Cartesian. And then we focused on a special type of reductive monoid. So a normal reductive monoid. So we always assume, okay, we always assume M to be irreducible, normal, and reductive. So a normal reductive monoid M is called very flat if pi M is flat. Oh, I only have 1 minute. I don't know, because all fibers of it are reduced to irreducible. And let me finish the part of, let me just at least introduce the Windbreak monoid and then just state the relation of this one with perfectness. So we look at the following category. So we fix a connected semi-simple group G0, and we define the following category MG0. So the objects are very flat monoids F, M, so this is F very flat, and its unit group, a unit group GM has derived subgroup G0M, which is isomorphic to G0. And the morphisms are those excellent morphisms from M1 to M2. So this excellent morphisms are from M1 to M2, and it restricts to an isomorphism from G0M to G0M1 to G0M2. And this is the theorem of Windbreak. So Windbreak showed that this category MG0 has a final object denoted by MG0. And this is the Windbreak monoid with respect to G0. So definitely we will not talk about the proof of this one. And we just need, so for the construction of this Windbreak monoid MG0. So because I am running out of time, so I'll first just from this, I will say its connection with the perfectness. So if you want to have something in this MG0, first you need a reductive monoid M with unit group G and derived subgroup just G0. Derived group of that G is G0. So Windbreak have the following theorem. So actually, so what we have first is, okay, I should explain that first. So, but maybe I'll omit that part. So a subset L of dominant weights defines an algebraic monoid or M with unit group G by this equation. So Km is equal to Kg of L. So here, this Kg of L here, so here, this Kg of L here is a direct sum of those Kg lambda for lambda in L. And this Kg lambda, so lambda is dominant weight, so Kg lambda is actually isomorphic to the tensor product L lambda star with L lambda. And actually, this is based on a decomposition of Kg. Actually, Kg can be written as a direct sum of Kg lambda for all dominant weights lambda. So this M, so actually all the algebraic monoid, all reductive monoid M with unit group G is defined in this way. And it's defined by a subset L of dominant weights. And the theorem states that a subset L defines such as algebraic monoid with unit group G if and only if L is perfect submonoid of this dominant weights and it is finitely generated and generating the weight lattice as a group. So that is the reason why we want to characterize this kind of perfect submonoids. And Windbreak used this theorem and he focused on a special case. Okay, so I want to mention is, so for this part, and for, it's just for convenience, we want it to be normal. And for this MG0, we want it to be normal. And at first Windbreak was trying to give a characterization for those reductive monoids, and he get this result. And actually, that doesn't require M to be normal. And then he focused on normal reductive monoids, and that provide him with a characterization for such L. And then, based on that characterization, he obtained the construction for this Windbreak monoid and the proof of this Windbreak monoid. So what he did is that actually he can give a characterization for those L when it is for those perfect submonoid, but it should, and also finite generated and generating the weight lattice as subgroup. And most importantly, if he require it to be normal, then that means that requires that L to be saturated. So that's the relation between this this theory of algebraic monoid with my results in perfectness and some efforts in characterizing this perfectness thing. Okay, I think I'm running out of time. I was going to talk about this construction, because this construction, the construction given by Windbreak, is somehow really, so if you really want to see this, I would say I really don't recommend his construction because it is too combinatorial and too complicated. And actually a better construction is given by Reductor in 1998, and I was going to talk about that, but I think I'm running out of time. And also, yeah, I think I don't have time for application of this Windbreak monoid thing. Okay, so I think that is it.
You done? Sorry.
I mean, actually, I prepared more, but I think it's already.
You can go over a little bit, yeah.
Okay, so I think I'll go over something you might be interested in, like the construction of Windbreak monoid. Well, I should say, actually, Windbreak gave a construction here, but that one is really, really impractical. So no one want to use that, honestly saying. So a much simpler construction of this was given by Reductor in 1998. So still, it's the simply connected case first. So we have that, we fixed that G0, right? So let T0 be the maximal torus. So we still, we let T0 be the maximal torus of this G0, and Z0 be the center of this G0. And then we let alpha I, now we'll maybe move, let alpha I be the simple roots, and rho I from G0 to GL VI be the highest weight, be those irreducible representations corresponding to highest weight omega I. So this R is the rank of G, so this is rank of G0. And we define the following group, G0 plus, to be the product T0 with G0, quotient by the diagonal embedding of D0. So this is a reductive group with derived subgroup G0 and center T0. So we can extend this alpha I and rho I to G0 plus. So we define alpha I plus from G0 plus to the multiplicative group from TG to, so alpha I plus TG is defined as alpha IT, and rho I plus from G0 plus to GL VI from TG to omega I W0 T inverse rho IG. So here W0 is still the longest element in the viral group of G0. So altogether, we get the following map: alpha plus, rho plus, which is the product of all these maps. Then it is from G0 plus to GMR product, the product of GL VI. And then we have that the Windbreak monoid. So it's indeed the image of this map, the closure of the image of this map in this set, or in this monoid. So this is a much simpler construction of Windbreak monoids, and actually, I think this one is the widely used one now. And the nice thing is actually this construction actually also works for positive characteristics. So remember we said, okay, we require that K to be of characteristic 1. But Windbreak's original proof only works for characteristic 1. But this construction given by Reductor and his proof actually works for positive characteristics. So this is a nice construction of this Windbreak monoid. So yeah, and this one somehow also nicely show you the abelianization of this one, which is just this GAR, which is just the alpha space AR. Okay, so this is the construction of Windbreak monoid. And I think for some applications of this, I will not spend time on that, and I'll just like provide you with some reference on that. So let me look at exactly the name of the student. Sure. So I'm not sure.
Yeah,
so the first one, yeah.
Yeah, maybe you should try to wrap up instead of going over too long. Yeah.
Yeah. Okay. So maybe I will. Okay.
Oh, I mean, you can finish the reference or anything. I just don't want to go too long.
Okay. Yeah. I just want to write down the reference for. Okay. So first, for the reference of Windbreak monoid, is just Windbreak's paper on reductive semigroups, and actually I cannot remember this reference clear. But for applications of Windbreak monoids, so one of the important application is L functions, basic functions, L functions. So that was done by Bouthier, Engel, and Saklaridis in 2016. So on the 4 more. Auric space of a reductive monoid. So in this one, they showed that they used Windbreak Monoid to find a generating series for some unramified local L functions. And the one is Boussier's paper in 15. So I think it is a paper in French. The paper in French. I think it is dimension of fibers. Okay, fibers. Oh, French. So it should be this fibers. So affine Springer fibers. Affine Springer fibers for groups. So the group version of affine Springer fibers. And also Jingren Chi's paper. I think that is called the geometry of Kotwitz Weyman varieties. Okay. So if you are interested in Windbreak monoids and its applications, so I think these are some references. It's major, I think those are some major applications of this. Sorry for keep this too long.
Okay, let's thank the speaker. I'm gonna thank for everybody. Yeah. Do we have any question, Lei? I think you had a question.
Yeah.
Okay.
So I have one thing is to check. Originally, in the definition of this the perfect submonoid, you also including the zero, right? The zero is inside of the L by definition.
Yes.
Okay.
Yes. But actually, we somehow that zero is somehow like definitely it fits in that definition, but we don't really need that because due to all those motivations, that is somehow a useless one, right? If you want to define a monoid, that will give you just a trivial thing, and if you want to use that to look at the tensor product decomposition, that is also like useless. So that fits with this definition, but somehow totally useless. Yeah.
Okay. So I have one question about your final theorem about the monoid is constructed by the perfect submonoid.
Oh yes, this one.
Yeah, the last theorem.
Oh, that is not mine. That is the.
Oh yeah, it's, no. I mean just the last theorem you're talking about. So, for example,
that is, where is that? Well, I cannot find that.
Yeah, it doesn't matter. I know the theorem.
Okay.
So my question is based on your characterization. We know, for example, even for like the GL4 or SL4 case.
Yes.
In that case, you proved that the L is corresponding to the subgroups of Z4.
Mm-hmm.
So basically, you only have 4 cases.
Mm-hmm.
So I'm wondering, in this particular example, you only have 4 perfect submonoid. You only have 4 L. So what are the monoids corresponding to?
What are the okay? So the thing here, it is actually something interesting here is actually in that theorem of Windbreak. Actually, there's one condition about generating that weight lattice as group. But for those 4 cases in SL4, so only the case for that being okay. Sorry, I should clarify for those theorems. So the theorem 2 and theorem 2 prime, that should be for non-zero submonoid. That should be for non-zero perfect submonoid. Sorry. my mistake. No, but that, indeed, I said something for this component supports. I think it's okay. So actually, this point here is in Windbreak's result, he actually required that you generate a weight lattice X group. And in those 4 cases, only the case if you take the whole group Z4, then it can generate that. Then you can generate that weight lattice, and for others you can't. And what will others give you is it will still give you a monoid, but the unit group of that monoid will not be G anymore. And actually the special case for that one is actually what they will give you are just some different type of just some, well, so you see SL4, so you mean the case when G is SL4. So this is simply connected, right? And you're looking at other groups, other semi-simple groups, which is a quotient of SL4 by a central subgroup. So that means this G prime is a semi-simple group which has the same Lie algebra as this SL4. Then that is the case defined by those other types of perfect submonoids of dominant weights. Does this answer the question? Hello?
Yeah, it's okay. Probably, yeah, I expect something like a more concrete.
Okay.
Just for the M, the way the theorems, I think it's the theorem 2 prime, the one you talked about. The theorem say is coming from the regular functions on the M, the monoid M.
Yes.
Expect is like, since this is a very explicit case.
Okay.
Probably have a more direct way to to see what is this M looks like. Instead of,
just
yeah, that's.
Do we have any other question? Okay, let's thank Chengze again. Yeah, thank you.
Yes, thank you.
Let me stop recording.
Let me stop recording.